Hello and welcome everyone. So we were on a discussion on the topic of linear algebra. So we discussed about a lot of things. We discussed about what vectors are and what are the operations possible. Just to remind you, I'll discuss two important operations to get the start going. The first operation is vector addition. Okay, and the second is scalar multiplication.
Sir, the board is not visible, sir.
Give me a second. These are two important operations on the vectors which I would like you to revise. This vector addition and scalar multiplication. You know, from computer science perspective, vectors are just array of numbers, and from physics perspective, whenever I say vectors, either an arrow should pop into a head or a dot in some coordinate system. Okay, so what is this vector addition? So if you have a vector v and its components can be v1, v2. Okay, so this vector somehow belongs to what's called as r2. Okay, y2 because it has two components, yr because the values that each component takes is a real number. If I have this vector v, let's suppose v, and I have vector w, so in that components are w1 and w2. Okay, now how to add these vectors? We have seen the addition in detail. I just would like to revise. This is the addition. You have to do component wise addition, v1 plus w1 and then v2 plus w2. This is the resultant vector. This vector over here is called as resultant vector. Just to remind, what is the resultant vector? So whatever these, what are the effect these two vectors produced? Okay, they'll have produced some effect. Initially v produced some effect and then w produced some effect. So this vector over here, the resultant vector, which I'll call r, let's suppose I'll call this r. So this r will produce that effect independently. So whatever these two vectors produce an effect, okay, one after the other. Okay, this vector, resultant vector, produce that that effect independently, and this is what. And we saw different properties of this vector addition. Okay, and now I'll go to scalar multiplication. Scalar multiplication was basically, if you have a vector like this, v1, v2. Okay, this was a vector, let's suppose, lying in some two-dimensional plane like this. If we have a vector like this, let's say this is the vector. If you multiply it with by number, let's suppose 2, so this will stretch the vector. I said it will either stretch the vector, squish the vector. Okay, so this is called as scaling. This effect is called scaling. Either stretching the vector or squishing the vector is called scaling. That's why this number over here, these numbers are called as scalars. They're called as scalars. Okay, just to show you, I'll write some code to show you the addition of the vectors, and I'll show you the scaling of the vectors. I'm going to the code. You can see it over here. So let's do the standard imports. Import matplotlib and import numpy. Not getting suggestions, I don't know why. Let me just activate the mode. Dot pyplot as plt, and then I'll say import numpy as np. I don't want to import pandas. So now what we'll do is we'll create two vectors, that these vectors v and w. So let's suppose v is a vector np dot array, but I'll just create a two component vector. Let's suppose 1, 2, something like this. Let's suppose I'll create a vector w. This vector is, let's say, 2, 1, or maybe 2, 8, something like this, 2, 4. If I have a resultant vector, how to show the resultant? So let's create a comment. So this is a resultant vector. So now r is equal v plus w. So now if I want to plot it, plt dot, so I'll plot them. Okay, this is the first vector, v vector. Okay, and then I'll plot w vector. Okay, let us start it from 0, 0. I want to show it and then we'll move it. This is w0 and w1. Okay, now if I want to plot it, let's suppose I'll say plt dot show. I first want to show this. Oh, these vectors. This is w, this is y. It is better to just have this. I'm putting these things over here. I'm limiting these x and y, and then let's change the vectors also. This is 3, -1 that I have used so that it is looking better on the screen. 3, -1 of the vector, and then the second vector is 2, 4. Then let's call this as a resultant, that there are no errors. Okay, so if I now draw this, This is how vectors look like. Okay, now you can see an x-axis here and a y-axis here. I have also highlighted the origin. Give me a sec. Okay, these are the two vectors. Now if I want to plot the resultant vector also, so how to plot the resultant vector? So I'll just plot it like this. Okay, so this is started from the origin, and then this is the component of first resultant, second component, and then this is angle xy. You already know all this syntax. So this over here is resultant vector. So I'll also put labels to these vectors so that they're also visible, vector w and vector v. Let's put the labels. Okay, label is this vector v and w. Now if you see this, so this over here, okay, by this vector, when I say this vector, so I will move on the x-axis 2 units and I'll move 4 units. So this is why I have called this vector as 2, 4, 2, 4. Okay, when I can write vectors like this. So this by default is a column vector, which I have told you this should be interpreted like this. But for the sake of simplicity, if I put these braces like this, so this should also be treated as a column vector. So this is 2, 4. So by 2 you mean you have to go 2 in the x direction and you have to go 4 in the y direction, and you will land at this vector. And similarly in here, so you have, when you go 3 units along the x-axis and then you go 1 unit down, so there's 3 minus 1, 3 minus 1. So this is the vector, the blue vector. So this is the resultant. I told you two methods of resultant. The first thing is parallelogram. So you just make a parallelogram out of this. So then this diagonal is basically a resultant. Or what you can do is you can just move this vector. You can move, let's suppose this red vector onto this. So this red vector is w. How to move this? So you can do that in this. So this w vector can be moved. So this is our w vector. Let's move it to the tip of this. So how to move it to tip? I just need to change these two numbers. Okay, now you can see that I just moved that vector. So this red vector was over this origin, but what I did is I moved. So this was tip to tail method. So this was, let's suppose, our vector v, this is our vector w, and this is our v plus w. Okay, so what you can do is, so initially you took, let's suppose, 3 steps towards the right by using this v vector, and then on this w vector, how many steps you took? You took 2 steps. Okay, that's 2 plus 3 is 5. That's why its x component is 5. Okay, that's why it's component wise addition. Then when you see the y component, so y component of let's take let's suppose first this vector. So this over here and this much over here. Okay, and that's why you add on the y components. You keep on adding the y components of both of these, and then you will land at whatever the y components were. Okay, so if you see this vector has an x component and a y component, which can be seen by the vectors if you perform the element wise addition. That's why here we have 3 minus 1 and 2, 4. So what should this be? So this is 3 minus 1 and 2, 4. So this vector should be at 5, 5 and 3. That's what the resultant vector should be at. Okay, I just moved this vector over here. If you see this. Okay, now I'll come to the scaling part. So I told you 2 operations are very important. One is this vector addition, and then we have this scaling or scalar multiplication. In scalar multiplication, what we do is you just multiply a scalar. It either stretches the vector or squishes the vector or maybe flips it also. Okay, that's why it's called as scaling. Let's take in the example. I'll just import the standard libraries and define a vector. So this is importing the standard libraries and defining a vector 2, 3. Let's have a scalar. Let's call it c. C is equal to something like this. This is my scalar, and then I'll say what is the resultant vector. So from here I'll also get resultant. I'll multiply this with c with v, so I'll get a resultant vector. Now again I'll plot these things. How to plot? Initially create a figure. Let's like this, create a figure. Oops. So I create a figure like this, and after this I'll plot these arrows. So this is the original vector. Okay, now I'll plot the scaled vector. So scaled vector, how to plot this? Same thing, but just keep in mind that this argument should be now resultant vector. So here I have given resultant vector, and now I'll just do the labeling part, labeling, limiting, and giving this legends, setting this x-axis and y-axis. So now you can see it. So original vector was this. Now I scaled it up. You can see it. The red is the scaled version. I doubled the vector. Okay, if I, let's suppose, have the scaling factor of 3, you can see this vector got increased 3 times. If I wanted -2, it will flip. Okay, -2 basically it will flick the direction and scale it accordingly. So here you can see this is the original vector. It flipped it and has the length of twice as much as this, but direction is opposite. So these are the 2 important operations in the vectors. One is vector multiplication, multiplication by scalar, and one is vector addition. Okay, now we'll come to the fundamental problem of algebra. Okay, if you have these things done, so we'll come to the fundamental problem of algebra. Let us at the screen. So fundamental problem of linear algebra. It's very important. Okay, very important. Now we'll sort of go into actual algebra. People usually start algebra from here, so they assume these details, whatever we covered in previous 4 sessions, they assume this data and then they directly start from here. So now if we can see, many of the problems they can be somehow formulated in terms of linear equations. Let's suppose I'll take the example of machine learning. So in machine learning, imagine you have a building, maybe you want to predict house prices. You might have seen in many people making this project, predicting house prices. Okay, so in this we have features like square footage, how much is the area, and then you have number of bedrooms and the proximity of amenities, how far is the school, how far is hospital from there, and other things like that. Okay, so there you have these features based on which you decide the price. Let's call these features as x1, x2, and so on till xn. Okay, let's suppose we'll multiply this with some coefficients. Okay, and then let's suppose they have some linear dependencies. Let's say we have some data like this. So we have 500 x1. Okay, let's say this is square footage plus 3x2. This is number of bedrooms, and let's suppose this is amenity some value. So we are saying this is 450. Okay, something like this, and we created this for one equation. Okay, so for 3 houses, let's suppose we have 3 linear equations. Okay, let's suppose this is our y1, y2. So this y1 is this is price. Okay, these are our features and this is our price. So now we are trying to formulate a real world problem in which we are trying to predict house prices based on these given features. Okay, and this is our price. So this is x1, x2, and x3. Let's suppose this is number of bedrooms, square footage, and amenities, distance of amenities. Let's suppose we have data for 3 houses. So this is first house. Let's suppose second house is following something like this: x1 plus 4 times x2 plus 0.3 x2 x3. This is equal to 500. Something like this. Okay, and let's say we have another house. Okay, for 2 times x2 plus 0.4 x3. This is equal to 400. Okay, so they do follow these equations. Let's say I'm saying that I have 3 houses. So based on their square, this is the square footage. Okay, and like this is number of bedrooms. There's a 342, and this is how far are the amenities, and we have come up with some number for that. So based on these features, so for each house we have constructed an equation, and this is the price. Let's suppose this price is 450k, something like this. Okay, now you have this data. You can see that we easily formulated this into linear equation. Why is this equation in the first? Because there is an equality sign. Why is it linear? Because each of these things is linear. So there is the highest power is 1. Okay, that's why it's called linear. Okay, and now you can see that 500, 3, 0.5. These are the feature values. Let's say this and this other feature values for the house 1, and this is feature value for house 2. And now what you can do is you can solve this equation to come up with values. Let's suppose this x1, x2, x3, and you can solve these equations. Okay, so I just showed you one fundamental problem which can be somehow shown as a problem. Now if you got these problems, so this is how one can formulate the problem. And the other way is that, let's suppose you have been given this x1, x2, and x3. Okay, and now what you want to do is you want to find this coefficients w1, w2, and w3. These are the coefficients. Okay, and let's suppose this is equal to something, and again w2, this is again w1, w2, and w3. These values of x1 dash, x2 dash, x3 dash. Okay, this is equal to something. Now you can see this. So this thing will be given to you. So this will be our data. This x1 comma x1 dash, these things will be your data. So that's what is given to you. And these w1, w2 are the coefficients that you will have to find. So these coefficients over here, they are called as parameters. Parameters that you have to learn basically. So you will have to give me, so anytime if somebody gives me x1 dash, x2 double dash, x3 double dash. So if they ask me how much does this house cost and what's the price, so I can use these parameters. I can just multiply this with w1 plus this w2 plus this w3, and I can give a prediction of the price. Okay, but this data will be given to me. From the data I learn about these parameters. Now you can see the first step was I formulated the problem with some linear equations, and then second thing was I took the data, used the data, and then calculate these coefficients which I call parameters in machine learning deep learning terms, and then I just gave you a prediction. So now does it ring a bell? Because I told you these equations we have been from, I think, lecture second we saw equation of line is w0 plus w1 x1 is equal to 0, something like this, or then we saw w0 plus w1 x1 plus w2 x2 is equal to something. So we saw all of these equations. This is for a line, this is for a plane. Then we say n dimensional equation is w0 plus w1 x1 and so on till wn and xn is equal to 0, and this is for a hyperplane which is n dimensional if you have n features. So here we have just one feature, here we have, let's suppose, two features. Okay, here we have n features. Now all of these somehow are decision boundaries, which we call decision boundaries. Decision boundaries, which they can be the decision boundaries, or we can say that these are curves. Okay, but they are planes, plane curves. Okay, so planes basically mean, so they just take the value of, they are linear. Okay, they are linear planes. So a line is a plane basically in 2D, and then we have this is the line is in 1D. Then we have 2D. In 2D we have these planes and we have hyperplanes, and all these equations we have seen. Okay, now you can see the connection. The first thing is we have a physical problem that is somehow written in the equations, and then we have been given some data, and then we have to find the coefficients basically. Is it clear so far? Is everybody following? Are you with me? Okay, now let's take a second problem. Let's suppose now what we can do is we can have some other machine learning, we can have some other model. Let's suppose neural networks. If you see, so in that you might have seen the diagram like this. Okay, something like this. I'll just make a random diagram and something like this. So here these things are the weights. Okay, these things are the weights over here. These weights are parameters, the model that you have to learn. Okay, now why does the algebra come in? Now, as I told you, mathematicians have this tendency, when they see a pattern in the problem, they say, okay, let's abstract the detail. We don't care about now what the problem is. So these things again can be written as equations. Okay, they can be written as equations. So these are the coefficients that you have to learn. So now what we can do is, if you see this problem, so now if you can just remove out these coefficients out, because that's the one that we have to learn. So what we can say is, in this pricing model, in this house pricing, so if I can write it like this: 500, 3, 0.5, okay, 700, 4, 0.3, 600, 2 and 0.4. So this over here is my weight matrix. You might have heard matrix. So I just do the coefficients, clubbed them together in this 2 by 2 grid, and this I call as matrix. Okay, similarly in this weights, in the neural networks, I'll have weight matrix, I'll have bias matrix, and accordingly I'll just I'll just put them together. So now the point is that mathematicians don't care about the details. They are saying, okay, you have a specific problem, but it follows a certain pattern. The pattern is that what I can do is, if I have these parameters to learn, and I have basically linear equations, let's develop maths for that without looking at the real world applications, because they abstract all the details. So now I just showed you two examples. I showed you one example of house prediction model from the machine learning part, and from the deep learning I showed you that there again are equations involved. I just clubbed these things that we have to basically find parameters, and we clubbed them in the matrix. But all the things that we will study in the maths will apply to these examples. Okay, mathematics is basically just the abstraction. So it has abstracted out the details. Okay, we don't care now what things that you are going to use and apply it for, but we'll just give you the details. Okay, that's the mathematician's perspective. Now you can see that we just formed these matrices from there, we have a 2 by 2 grid. We call them as matrices. Now let's suppose I'll start with simple equations. Let's be the mathematician for some time now. Let's say we have an equation like this: 2x minus y is equal to 0. So this x and y, this can be data, and this is, let's suppose, these coefficients are the weight matrix, something like that. This is minus x plus 2y is equal to 3. Okay, now we have two equations in two variables. That's why I call this fundamental problem of algebra. So fundamental problem of algebra. Why is this called fundamental problem? That's why algebra is there for. You have to find the values. Let's suppose you can even swap them. You can say this 2 minus 1, 1, these are data. This x and y, there are w1 and w2s. So if you see, this is the equation of line. If you can remember, we had w0 plus w1 x1 plus w2 x2. This was equal to 0. So this was equation of a line. Okay, so if you can see over here, this is the equation of a line. Okay, now the question we have is, if we have been given these lines, so now we have to find solutions to this, so that both of the equations get satisfied. By satisfied, I mean when you plug these values, so this equation should get satisfied and this equation should get satisfied. Okay, basically think it like this: we want to find these x's and y's, and in our terms, let's suppose if we have example, let's suppose this data is given to us, this x1 and x2 are given to us. We want to find this w1, w2 in terms of machine. We want to find these weights of the model. We want to find the parameters of the model. Okay, so let's suppose we start with these equations. Okay, this 2x minus y is equal to 0, minus x plus 2y is equal to 3. So these are our equations. Now what we can do is, if I just I can show you different sorts of pictures in this. So the first picture that we will see is, I'll call that, let's suppose, a row picture. So we'll take a row at a time and we'll try to plot it. Okay, let's suppose I'll take this over here. Okay, and these are my equations. I just want to keep them handy. These are my equations. Now if I plot this is a line, so everybody agrees on this is a line and this is a line. So I'll see where they intersect. So wherever the intersection point is, that is my solution to the equation. That's my solution to the to these set of equations. Okay, now let's go to code and code these equations, and we'll see what we'll get as an output. So I think the first thing is, I'll have the standard imports, import numpy at matplotlib. Okay, and then the first thing is, I'll create some x values, because I'll have to create two lines. So this is my x value. So I am saying x value np.linspace, give me values from -4 to 8 and give me 100 such values. Now if you see the first equation, is 2x minus y is equal to 0. So this is the equation. So let me just write it over here. So this is the equation. Let me comment it. So now if I just rearrange it, I have the x values. So what I can say, y is equal to 2x. So now I'll just say y1 is equal to 2x. So x are the x values. So I'll say y1 is equal to 2 into x values. Okay, everybody agrees on this. So this is how I have x and I have y. So this over here, this is a complete equation of that line. I have the x values, y values, because I want to plot the line. Okay, now let's suppose I plot this line. I'll plot this line also. PLT, this is the figure, and now I'll plot this line. So PLT.plot, and then I'll give the coordinates as x values, y values, and this label is written in latex. So this is 2x minus y is equal to 0, and I'm giving color blue. And let's suppose I just want to set up the graph. So let me set it up. You can see this line. Okay, this is the line 2x minus y is equal to 0. Now the second line that I have to create is where the equation basically was I think x minus x plus 2y is equal to 3. So this was the equation. So when you solve this equation for y, you will get the y values. So okay, I'll directly write the y value. So equation 2 is like this. So I'll rearrange the equation 2. So this was equation 1, and this is my equation 2. Oops. So this is my equation 2 over here. So it was minus x plus 2y is equal to 3. When I solved it for value of y, this is x plus 3 divided by 2. That's what I did over here. This is my y2. Now I'll plot for y2. Okay, plt.plot and x values, and again y2 value, and now this is minus x plus 2y is equal to 3. This is color red. Now if you can see, they intersect at certain point. Okay, they intersect at a particular point. If you see the point over here, this point is 1 and 2. Okay, the point is 1 and 2. Wherever they intersected, that means this point satisfies both the equations. So if you put this value, of we have 1 comma 2, 1 comma 2. If you put these in these equations, so it will satisfy both the equations. 2 ones 2 minus 1, this is 0, and it satisfies this. Okay, so this is 2 multiply 1 minus 2 is equal to 0 for the first equation. I'm just giving one value instead of x, and instead of y I'm giving 2. So for this is minus 1 plus 2 into 1. So this is 2 into 22. So this is equal to 3. Okay, this equation also got satisfied. So this point over here, this solves both the equations. This is the solution for these two equations, if you see it graphically. Okay, so let me again draw this point also. So you can plot this point by just saying PLT and say intersection point. So this intersection point is 1 and 2. So I'll just write it manually, because I know this point. Now the question is, we have to solve this. I'm just making the visualization for the first thing, and then maybe we'll have to solve these questions, solve these equations. So right now I directly got the answer. Intersection x and y is 1 comma 2. I'm plotting it. So this is the solution point, 1 comma 2. Okay, this is one way of looking at it. You can see you have a line and you have underline, and when you just take a row at a time. So you took row at a time. You took one row at a time. Oops, what's happening? So in this equation, the initial equation was this: 2x minus y is equal to 0. The other equation was minus x plus 2y is equal to 3. So you took the first equation and you drew a line. So this is the line. This blue line is the line for the first equation, and then you drew the second line over here. So then you saw where did they intersect. Okay, and then this intersection point is the solution of this. Okay, we can do it same with the 3D. If you have a 3D equation, you can do, and this is why I call it row picture. This is row picture. Why? Because we are taking a row at a time. So we are taking this row and plotting it. We are taking the second row and plotting it. Same thing, let's suppose if we have some three-dimensional equation, I'll also write that three-dimensional equation. Let's suppose the equation is x minus 2y plus z is equal to 1. 2x plus y minus z is equal to 3x plus y plus z is equal to 3. Pardon my handwriting if it is not visible. Let's change these coefficients. Let's change them to some values, that because I have to show you something. Let's keep them as 1, 2, 3. Let's change this. So this, how can I change it? 1, 4 and 8. Okay, 1, 4, 8. I changed it somehow because I have to do something with it. This is x minus 2x plus, and this is 3x plus. So these are my equations. Now you can see this resembles this equation: w0 plus w1x1 plus w2x2 plus w3x3 is equal to 0. So they resemble this. So now you know each of this equation over here is the equation of a plane. The equation of a plane. Now if I draw these, they'll be these will be planes. Okay, let me just hide this code. Now I said these are my three equations. Okay, and I have three equations and three unknowns. Now my job actually is to find the solution which satisfies all these equations. Now this you know from the previous lectures that each of this is equation of a plane. So now we have three planes, two planes. If they intersect, they'll intersect in a line. So one plane will be something like this. Okay, let's suppose some other plane is like this. So they'll intersect in a line. But three planes, if they are which you call a non-planar, if they don't lie in the same plane, so they'll be intersecting at one point. Okay, so, and we'll have to find that point. X, y, and z values are to be found. Okay, let's again see the row picture. So in the row picture, the first thing is we'll draw this plane, and then we'll draw this plane, and we'll draw this plane. Okay, that's how the way to look at it. So whenever you see some equation, the first thing that you should, if it's a 2D equation, there are two lines. Now if it is 3D, that there are the three planes. And now if you have to think in 4D, you can't imagine in 4D, but the mathematics gives you tools. Everything in the story remains the same. The whole story remains the same. The only thing is you probably can't visualize. You have to think of a four-dimensional space, and you have hyperplanes that intersect in a line or something. Okay, let us see this row picture again. Let's see the row picture, and I'll go to the code window back, and let's make these planes. Okay, the first plane was x minus 2y. Let's make these planes. I'll have the imports. Import numpy as np and matplotlib and for this 3D axis. Now what I can do is I'll define x and y values. Okay, and I'll define z values I'll get from the planes. So now you have this x values and y values. Now what I can do is I can just create a mesh because I am drawing the 3D surface, and now we have the first plane. So based on the first equation, I'll just define it over and I'll explain it. Do you see? Oops. So over here the first plane was this. Now I have my x and y values. I am calculating z value from that, so which I am calling as z1. This is for plane 1. Okay, similarly for the plane 2 I have this. So this is my plane 2. Okay, plane 2 was this equation, and I solved it for the z, and z was like this. I just said 2x plus y minus 2. That's what I got from mathematics. I just rearranged the terms, and now we'll come to plane 3. Okay, now you can see that this is my plane 3. This was 3x plus y plus z is equal to 3. I rearranged for the z term and got the values of z3. Now I have to plot them. Now you know that each of the z1, z2 and z3, there are three planes. Okay, there are three planes. So now I'll just create this plotting first. Okay, figure plt dot figure, and then you know all of this. And the first, I'll create a surface. I'll show you the first plane. Okay, let me just set the labels: x label, y label, and z label. You can see this is the first plane. It goes something like this. Okay, and the second plane is something like this. Let's plot that also. Okay, I think this should be easy to plot. Okay, this is my second surface, and this is my third surface. Now if I just draw the second surface, you can see this is the second surface. They somehow intersect in a line. Okay, when I draw the third plane, you will see them intersect at a point. Okay, and it is very scary now. The more planes you get, the figure becomes much of a jumbled one. So now what you can see from the row picture is that when you take one thing at a time, you take one row at a time. If it's a line, you can draw lines, and two lines intersect at one point, you can say that's the solution. Okay, when you take the things in 3D, they are planes. If you have three planes, they'll intersect at a point. Okay, and that's what you see. But now you don't have capability to imagine the maybe hyperplane, the plane in 4D. Okay, you can see this plane which is in let's suppose 3D, which is a 2D plane and is in 3D. Now we have hyperplanes, we cannot imagine them, but the mathematics gives you power to still compute those things. Okay, this is what I wanted to tell you about the row picture. So for how many of you is this row picture clear? Whenever you see equations, you basically see these rows, and there are different ways to visualize this. Is it clear? So one way is you take column at a time and you just plot these things and you see the intersection point, and that's how you should imagine. When I write equations, you can either think of this, but now you can see the problem with this row picture is that you can't imagine much more higher dimensions, and it becomes really problematic to make it. Okay, now the second picture that we can see is, that picture is called as column picture. Okay, again coming back to the same equation. Okay, let me just hide this code. Come back to this. The equation we had was this initial equation in 2D. 2x minus y is equal to 0 minus x plus 2y is equal to 3. So why I called the first one row picture is because I took one row at a time. Now what I can do is I can write it in the matrix notation. I can take these coefficients out. So I can say 2 minus 1 minus 1 2, something like this. Okay, then I can say x y, and then I can say 0 3. Okay, can you see this? So this over here is called as coefficient matrix. Okay, so this is matrix of unknowns and this is my B. So I can write it A, this matrix over here is A, and this is X and this is B. So I can write AX is equal to B in the matrix shorthand notation. I can write it as AX is equal to B. A is my this matrix, X is my this, and B is my this. Okay, now what you can think is you can take each of this column over here. Now each of this column is like this. 2 minus 1 is one column. Okay, from this. So this 2, this coefficient matrix 2 minus 1, and minus 1 2 is the other column. Minus 1 2 is the other column. Okay, then I have this solution that I want to get. The solution is 0 3. So what I can do is I can say this x and y, I can just write it as a scalars x and y over here. Okay, now I have to find this x and y. Basically I have to take some combination of this x and y so that I land at f0 and 3. Now this can be treated as vectors. Okay, I can make these vectors. Okay, let's go to the code and draw these vectors. So vectors are 2 minus 1 minus 1 2 and 0 and 3, and I have this x and y. How should I combine these vectors to get to the 0 comma 3? Okay, let's see this row picture. Row picture is more neater. Okay, and it's loved by the people who are from computer science because they always see it as vectors. They don't see this row picture. They usually see column picture because column picture is more neater. It just gives you vectors. Okay, let's draw it. Okay, standard imports, again the same thing, and I'll create these two vectors. This is my import statements, and now I have a column vector and column vector second. So this is my A column vector. Oops, not copying exactly. So A column vector 1, column vector 2, because the matrix is 2 minus 1 minus 1 2. This is what I have created. Okay, this is my column, first column, and then now I have second column from the A matrix. Now this is my B matrix, so that's the AX is equal to B. So this is my B. Oops. Okay, this is my B. 0 comma 3 is my B. Now I'll plot them. Really easy to plot. Not difficult. By now you should be experts in plotting. If you are not, I'll have doubt on your capabilities because we have done so much plotting. So now if you see this, I drew two vectors. So I drew this vector. Okay, this is a vector, this vector 1. Okay, if you see over here, this is my vector 1 and this is my 0th vector, basically first column and the second column. Now I have to get a resultant vector. Okay, let me draw the resultant vector also. The resultant vector is 0 3. Let's draw that. To draw this resultant vector, let us just, because this is a resultant vector B, so I draw this B0 B1. So I hope now I will get this is my resultant vector. So another question is how to reach here. So I have to reach here. Okay, and now what I want to do is I want to take this vector and this vector, sum them in a certain way to land at this vector. Okay, that's my job now. I just want to land at this vector. Can I do one thing, because you know addition? So how to perform this addition is, so what you can do is, if you somehow take one of this, so one of this vector, okay, and you take two of this vector, let's suppose I'll take two of this. So one of this green vector is this much. Okay, let's say this much. I'm terrible at drawing, but I'll fix that drawing with the matplotlib. So this is my green vector over here, so which let's suppose is this much. This is the first, and now this is the second vector. So this is 1 times green and this is 2 green. Okay, now when I'm putting 2 green, I'm taking one of this blue vector and two of this green vector. I'm landing it here. Okay, now let me show it. Let me show it exactly what I mean. I'll show it in the code. It's too bad in the drawing. That's why I'm a computer science major, not art major. So now what I'm saying if I just multiply this A vector, if you see, this is my A vector and 0th column, and this is my A first column. So minus 1, 2, the green vector, I'll multiply it 2 times, or I'll multiply it by 2. So I'll multiply this green vector by 2. Okay, basically the first column. So I multiplied the second column rather. I multiply column second by 2, and now what I'll do is I'll just plot it from this. I'll plot it from this. I'll just shift it. That's what I'm doing over here. Can you see it? To reach the resultant, what I did is I combined these two vectors somehow. I took one of this vector, one of the blue vector, and 2 of this green vector, okay, to land at the resultant vector. So that's why if I again show you the equation, just going back to making this code like this, so over here. So we wanted to see how to mix these vectors so as to land up with this vector. I said, okay, take one of this vector. Okay, take one of this, that means 1 multiplied by 2 minus 1, and take 2 of this, minus 1, 2, and you will land at this 0, 3. So if you can just calculate, you can see it. So 1 multiplied by 2 is 2, minus 2, this is 0, and this is minus 1, plus 2, this is, have we written something wrong? This is 4, yes, it's 3. I hope you are able to calculate it. Pretty easy. This is 2 minus 1, and this over here is minus 2, 4. So this gives us this. So this I am taking 1 times of this vector and 2 times of this vector to land at this vector. That's what I showed in the visualization also. So if I go back to the visualization, what I did is, initially, if I just remove this, if I just remove this 2, I'll put a comment in here, and I'll start these vectors at 0 and 0. Okay, let's do that. Start at 0 and 0. So this was the initial condition. So I had a green vector and I had a blue vector. So basically I had these two vectors which were in the coefficient matrix. I said how to somehow mix these two vectors so as to land up at this vector. I said take one of this blue vector and 2 of the green vectors so as to land at this, because you know how vector addition works. So that's what I did. Multiply this by 2 and multiply this by 1 and then just plot it. That's how we landed here. Okay, the same equation was solved by 2 ways. The first thing is we draw a line and saw where they're intersecting. That was the column picture. That was the row picture. And we took a row and then drew a line and then saw where they intersected. And the second picture which I said is just take out these columns out and think these columns, treat these columns as vectors, and then see how to combine these vectors together so as to land up at the resultant vector. Is it clear? Is it clear? Are there any questions on this?
सर एक और बार ये समझा देते सर.
So what I was saying in the column picture, let me again without this code. We have 2 ways to look at this equation. The equation that we had is this was the equation. So equation was this: 2x minus y is equal to 0, 2x minus y is equal to 0, and the other equation was minus x plus 2y is equal to 3. Minus x plus 2y is equal to 3. I said there are 2 ways to look at it. The first way is row picture. You take one row at a time, because you know each of this is a line. So if it is with 2 of these variables, you can draw a line. So when you draw the line like this, so you have a coordinate system, and then you draw one line and the other line. Okay, this is the solution. This over here, this is the solution. Okay, and similarly in the 3D, you have these planes. You can draw the plane and see why they are intersecting, and that is the solution. And now I said the other way to look at it is like this. So you have 2x minus y is equal to 0, minus x plus 2y is equal to 3, something like this. Okay, and now what you can do is you can make it a matrix: 2 minus 1, minus 1 2, okay, and x y, and this is 0 3. I just rearrange these things into matrix notation. This is my matrix notation. Both of this and this represent the same thing. So whatever this represents and whatever this represents is one and the same. Okay, they're the same things. So but this is in the matrix notation and this is in the equation notation. So I call this A and I call this X and I call this B. I said Ax is equal to B. Now what I said is I have to find this X and Y. So how I can do it? I said X multiplied by 2 minus 1, because now you can see this is scalar multiplication, plus Y multiplied by minus 1 2 is equal to 0 3. Now I have to combine these vectors somehow. I have to combine them in certain proportions. I am saying take one of this and take 2 of these. You land at this. So that's why I said take one of this and 2 of these, and you land at this 0 3 vector. Okay, and this is how I'm taking combination. I'm taking one of this and 2 of this to land at this. Okay, and that's why I show these vectors. So you had vector initially vector this. So our one vector was something like this. So other vector was something like this. Okay, and the resultant that we wanted to get was something like this. Okay, something of this vector. What I said is I said take one of this okay, and two of these vectors, two of these yellow vectors, and you will basically land it here. So this is 2 of yellow vector and 1 of this vector. So when I took this combination, when I took one of this, let's say this is purple or whatever it is, so this color, and 2 of this yellow vectors, I ran it at this vector because I can freely move this vector, okay, and this 1 and 2 is basically the solution. That's what was the solution that we got even when we were intersecting these lines. Is this column picture clear now? So we can think these columns as vectors. The question is how to find these points, how to find the solution. So there are a lot of methods by which you can find the solution. Elimination methods are there. You can find the solutions by using inverses. You can find the solution by using determinants. But right now we are at the part where I want you to understand. I want you people to understand when you see these equations, how to think about the equations, how to imagine these equations. That's very important part which many people miss about algebra. Okay, they think we can solve it. If I just show you a mechanical method, very easy to solve. I'll say, okay, these are the operations that you do. But it is better to know what you're doing. Okay, and we'll land at how the matrix multiplication is done in a certain way, and all these concepts will be clear once you are clear with this. Now, okay, less of a code, I'll show you more of more things in written. So now the equation that you saw over here is this. So you had x multiplied by 2 minus 1, okay, this was x, and then plus y, and this was 1 minus 2, okay, and then you had to get to 0, 3. Okay, basically now if you see this, what I want to take is I want to take some combination. Okay, so this combination is called as linear combination. Okay, how to combine these vectors, somehow so that I land at this vector, because these are 3 vectors. I have 2 minus 1, 1 minus 2, and I have to get myself at this vector. That should be my resultant vector after, because that's why the scalar multiplication and addition was important, because if you see, these things are just scalar multiplication and addition. So what combination should I take so as to land at this vector? Okay, that combination is called as linear combination. Why linear? Because you are just taking linear, you are not giving it in the powers. So linear combination of vectors, let's now again generalize it. Let's call this vectors v1, let's call this vectors v2, let's call this vector v3. Mathematician has tendency of generalizing. Now if we have vectors v1, we have vectors v2, and we have vectors till vn. Okay, some vectors like this. Now we have a vector some v dash. Okay, so if we take a combination of these, so we take combination like this, c1 v1 plus c2 v2 plus and so on c and vn. So whatever vector we land at over here, so this is called as a linear combination. This is called as linear combination. How do you combine these vectors? Okay, so then we say, are we able to go to this vector? Okay, are we able to go to this vector by taking a linear combination? Then we'll come to the word which is called as span. What is the span of this vector? Okay, now we can see that if we have a vector, only one vector, let's suppose we have vector v1 only. So if you multiply it with any scalar, so v1 is something like this. Okay, so what you can do is you can just get a line out of this. You can just get one line. So if you have a vector, you can either move forward, you can move backward. Okay, you will basically get a line, something like this. Okay, from a vector, if we have a vector v1, some vector like this. Really bad at drawing. Even my hand is not steady. Okay, this is v1 vector. So if you multiply this with any scalar c, you can just either scale it up, squish it down, basically what we call it scaling. Okay, that's how these are the vectors reachable from this vector v1. Okay, which vectors can you reach? You can reach over here. You can, all of these things are vectors in the space. This is in R2. Let's suppose we have an R2 over here. This is my R2. That's why I choose matplotlib to draw. And now if you take multiple vectors, you have vectors v1, you have vectors v2. Okay, now if you combine them in certain way, okay, you said c1 and c2. Okay, you give the values to land at certain vectors. Okay, that's what is called as linear combination. Is it clear? Is the linear combination clear? Now we'll come to the span of these vectors. What is span? Pretty easy concept now. So whatever vectors are reachable through the linear combination is called span. Okay, you have vectors v1 and v2. If you take the linear combination c1 plus c2, okay, which are vectors are reachable from here is called span. So what is the span? The span is the set of all the possible vectors which are reached by the linear combination. Or when you take the linear combination, whatever vectors you make, that's called the span of these vectors. So if you have vectors v1 to vn, so what is the span? So take all the possible linear combinations. So this is called as the span of the vector. And now we'll see the span. Let's suppose we have these vectors. We had the vectors 1 and 2. This minus 1 and 2, and I think just lost the track. So here we have 2 minus 1, 1 minus 2. This is 2 minus 1, 1 minus 2, something like this. Okay, so these are my vectors v1 and v2. So what are the vectors that are reachable from here? Okay, what vectors are reachable from here? I can say c1 multiplied by this plus c2 multiplied by this. All the vectors that are reachable from here, that I'll call a span. With the first thing that we saw is the linear combination, how to combine these vectors together so as to reach a particular vector. Then we saw span. Span basically is all the reachable vectors by taking the linear combination. That's called a span. Okay, let's do that. Okay, let's do one thing. I'll take two vectors. I'll take vectors 3, 4, 2, 8, and I'll see their initially I'll see linear combination. Let's write in the code. Most things I'll show in the code so that it's pretty understandable to you people, so that you don't miss anything. Again, starting with the imports, and then I'll have two vectors. I'll have vector v1. Okay, I'll have vector v2. These are my two vectors. So you know how to draw them. Pretty easy stuff. These are my two vectors, 3 and 4, 2 and 8. So these are my two vectors. Now what I can do is, let's plot them. Let's say we'll plot them. Let me plot that.
Sir, the coding window is not visible.
Thank you so much. I'll just make it visible. So you can see I just plotted this thing. Initially I imported these matplotlib and numpy. Then I created two vectors, 3, 4, 2 and 8. And then I plotted these things. Okay, I'll just format the plot. Okay, and these are my two vectors. Okay, now I want to take a linear combination. Let me just define v3. So v3 will be a combination. Let's suppose v3 is equal to some combination, 2 times v1 plus 3 times v2, but I should just add multiplication in between so as to abide according to the Python syntax. Then I'll just plot this v3. Okay, so now this v3 is the linear combination. So this v3 vector, so this is 2 times v1 and 3 times v2. Let's make it only one time so that it is visible on the screen. Otherwise I'll have to limit it. So this will be one time and this will be 2 times. Let's say I'm taking a linear combination. Okay, if you see this again going out of the screen, the problem is that because this is pretty big number. Okay, so what I wanted to show you, this red vector over here is the linear combination of these vectors. So this blue vector and the green vector, when you combine them in a certain way, you get to a vector. Now what I want is, I want to take all the linear combinations, whatever is possible. So can you guess what will be the linear what will be the all linear combination? Where can I reach? Can I just go through all of the vectors in the 2D? Who agrees on this? By taking the linear combination of this blue and green vector, do you think that we can go to all the vectors? Basically we can span the whole 2D space. It's pretty easy to see. So you can see this. So if I just draw how to now do that, what I can do, I'll just define some scalars. So I'll define scalars. Give me a second. So you can see over here. Just remove one linear combination. I'll make a lot of linear combinations. How to make that? I'll just scalar, make some 20 scalar values, and then span of vector v1 is this. If I just want to show you the span, this is span of vector v1. Okay. So now if I have to just, let's suppose, say the span, what will be the span of the vector? Only one vector. So if you just take one vector, let's suppose you take only this green vector, what will be the span? Can you answer this question? Very obvious question and very easy to answer. The span will be the whole line. It will just go through the line because you are stuck. You cannot go out of that line. You can just scalar multiply it. That's what I am doing over here. So scale s multiplied by v1, and s is the value in the scalars. So if I have span of vector v1, that's only that line. Okay, if I just draw it, let me draw it. So how can we draw it? So for let's suppose vector in span of vector v1. So what I did is plt.cure and start from 0 0, take the initial of this vector 0 and then vector 1 and then make this is the span. You can see there is a red line over here. Okay, you can see this is the span. Okay, this span is for the blue vector v1 vector. So this is the span. If I do the same thing for span of vector 2. Okay, span of vector 2, again the same thing. I just need to check now this vector 2 has to be changed to show you the span. Now the span of this green vector is the simple line. Now I want to take linear combination of these. So what I can do is, I just created two. Now I have to combine them linearly. So how to combine them? I'll run two for loops. For vector 1 in, I call this vector 1 in v1, and then I'll say for vector 2 in this, and then what I'll do is I'll just add these things to it because I want to take all the linear combinations. This is vector 0, vector 1, so I'll just start it from 0, 0. That's why this copilot fails. So I'll take vector 1 plus vector 1 of 0, because I am adding this component wise. Do tell me if you understand this line. Vector 1 of 1, and then I am adding them together. Basically taking the linear combination. What I have done is I have just taken 20 scalars. So I have taken 20 scalar values, multiply that 20 with this, multiply that with v2, just taking the combination, and now I can show you this 20 should not be bigger. Okay, you can see a lot of vectors in the span. But if I take all the numbers, all the infinite numbers possible, you can see whole of this space getting filled. This over here is span of this, but this is partial span. This is not a whole span. If I just increase these numbers, you can see that all the vectors that are in 2D can be reached. So this is the span of the vectors. How many of you understood span? Okay, so what I said span is that whatever vectors are reachable from that vector. If we have a vector, the span of that vector is, if you take a combination of, if it's single vector, you just scalar multiply it. You are stuck in the line. But if you have two vectors, you take all the linear combinations and you can reach different vectors. And all these vectors which are reachable by taking the linear combination is called the span of these vectors. So I showed you the span over here. Okay, so when I took this, I had a vector initially. So that vector was this 3, 4, 2, 8. When I just decided to go with 20 scalars, but you know that this is uncountably infinite numbers are possible here, because scalars you can take any real number. But I just took 20 values, and after that I multiplied each of the scalar with vector v1 and multiplied with vector v2, and then ran 2 for loops. Within that 2, what I did is I just created these vectors. Now this vectors looks too boring. What I can do is I can just create dots instead of these vectors. Okay, so how to do that? plt.scatter. Okay, vector 0 and vector 1. So I will not create this, so you can see these dots. Okay, so this is the span. I told you two ways to look at the vectors. Either look at these as dots or these vectors which are these lines having pointed arrows. So these are 20 values. So let's suppose if I create some 25, so it will be multiplied 25, 25. So it will be more. Now you can see more dots on the screen. If you just want to cover all the dots, you have to give uncountable. You can see more dots on the screen now. Okay, so basically all the points that are on this 2D surface are reachable by these two vectors. So these two vectors are called as linearly independent vectors. I'll tell you what this linear independence means. So can I assume that you guys know span now? So we'll do one more example of column picture, okay, with the 3D now. So initially we were in 2D, we'll do it 3D, and I'll use, instead of code, I'll use my art, and that will be terrible, but the equations were here. The equations were something like this. Equations were x minus 2y plus z is equal to 1. Okay, I'll write a little bit detail. 2x plus y minus z is equal to 2. And then I have 3x plus y plus z is equal to 3. I think I changed these values. These values was 1, 4 and 8, something like this. Okay, now how to write column picture? Okay, we saw column picture in 2D, but now we'll see column picture in 3D. I'll make a matrix. How to make that a matrix? 1, 2, 3, minus 2, 1 and 1, and 1, minus 1 and 1. Okay, and then we have x, y and z, x, y and z, and then we have over here 1, 4 and 8. I can call this a, I can call this x, and I can call this b. Okay, these are my columns. So now the question is, what combination should I take to reach here? So I am saying x times of this column 1, 2, 3, 1, 2 and 3, plus y times the other vector, that is minus 2, 1 and 1, minus 2, 1, 1, plus z times 1, 1 and 1. I think one of them was negative, probably the second one. Yes, and this is equal to 1, 4 and 8. 1, 4, 8. Now think each of these is vectors. Think this is a vector, this is a vector, this is a vector, but in 3D. Now we have these vectors in 3D. Okay, so what linear combination to take to land at here? Okay, if I can just eyeball it, so I'll say take 2 of this, 1 of this and 1 of this. Okay, let's say 2 multiplied by 2, this will be 2, 4, 6, plus minus 2, 1 and 1, plus 2 minus 2, this is 1 of this is only 1, so 1, minus 1 and 1. So I am taking 2 of this vector, 1 of this and 1 of this, so you can land it here. So 2 minus 2, 0, this is 1, 4 and this is 0, this is 4, 6, 1 plus 1 is 8, yes. So if I take 2, 1 and 1, this combination of these vectors, if I take this linear combination, I land here. Okay, and now this is the solution. This x, y, z, the value is 2, 1, 1, this is the solution. As I said, there are different methods of finding a solution. Right now, you should tell yourself how to think about these. So I am taking some certain linear combination to reach this vector. Okay, if I draw this 3D, I'll just copy and paste the code, and then you can just, maybe while watching revising it, you can pause the code and then write it for yourself. Again, the same stuff that we earlier did, but now here this is in 3D. So if you see this, I computed this v1, v2, and then b, and then I'm doing this. So you can see these three vectors. Okay, this vector is vector v1, vector v2, and vector v3. There are four, and this b is the solution. This b is where I have to reach. I have to take linear combination. If I just remove this b looks a little bigger. These are there is a small vector. This v3 is very small. Okay, and then we have this v1 and v2. This is in 3D. Okay, and I have to take a linear combination in order to reach this b vector. Okay, what linear combination I took? I took 2 of the first vector and 1 of the other vector, and to land at this vector b. That's what I showed you in the diagram itself. So when I was showing you the diagram over here, so this is a vector. Take 2 of this vector, take 1 of this vector, and 1 of this vector to lead at this vector. So this vector is in the span of these vectors. So what is the span now? So span is basically what when we take all the linear combination and what are the possible vectors are there. So that's called the span. So span is a set of vectors. Okay, which are reached when taken linear combination. I'll just write in the shortcut because I don't believe in definitions. Okay, you should understand this thing, and then it is better to understand rather than to just remind the definitions. So what I'm saying is span is the set of all the vectors which are reachable when you take all the linear combination. Then comes the concept of dependence and independence. And what is that? Let's suppose if you have vector v1, and then you have vector v2 and a vector v3. Okay, so if I take a linear combination of these vectors, some linear combination, let's suppose c1 v1 plus c2 v2. Okay, and I am able to get this vector v3 somehow. Okay, then I'll call these vectors as linearly dependent vectors. Why? Because this v3 is somehow reachable. So how I can write it? This is c1 v1 plus c2 v2. I can write it. I can get this somehow c3 v3. So how I can write it? I can say c1 v1 plus c2 v2 plus c3 v3 if this is equal to 0 mathematically. Okay, if this thing is equal to 0, then I'll call them, they are linearly dependent vectors. So linearly dependent. Now you have to reason about this. Why I just took this c3 over, I did not make it minus, because I'll just bring up some other constant. I'll call it c3 dash, something like that. Okay, so if this equation is followed, that basically the notion of this equation is if I take two vectors and I cannot come up with the third vector by taking any combination of these vectors, then they are called as linearly independent. But in this case, if I take some combination of v1 v2, I can come up with v3, so that is linearly dependent. Or it can be other way around. If I have vector v1 v2 v3, if I can take any two vectors and I can get the third vector by taking some linear combination, then I'll call that as linearly dependent vectors. Now the reverse cases, if I am not able to get the vectors, let's suppose if I take these two vectors and I am not able to get this v1 vector from these, or the same cases, I'll take these two vectors, I am not able to get these vectors, so I'll call these vectors as linearly independent vectors. Okay, so basically the thing is, so c1 v1 plus c2 v2. Okay, this should never let's suppose I cannot construct some v2 vector from it. Okay, you can just put it mathematically the way I put it over here. Now you can see this, if I have vector 1 0 and 0 1, are they dependent or independent? They are independent. Why? Because I cannot take any combination of this vector to reach here. Okay, if I take any combination, let's suppose if I take 2 multiplied by 1 0, it will still land me at 2 0. I can never make this 0 and 1. I can never make this 0 as 1. Why? If I multiplied, scalar multiplied, not possible, because you are multiplying with 0. Okay, if I let's suppose have this vector, if I have vector this, I have vector 1 2, I have vector 3 4, and I have another vector, let's say 5 8, something like this. So this is my v1, this is v2, and this is v3. Now these vectors are linearly dependent. Why? If I just take this v1 and multiply it with 2, okay, and take 1 times of this 3 4, this will be able to give me this vector. So this is 4 plus yes, this is 2 plus 3 is 5, to 4 plus 4 is 8. Yes, so now this set of vectors over here is linearly dependent vectors. So linearly dependent vectors. Okay, this over here is linearly independent vectors. Linearly independent. Okay, now the question is, why to think so much about independence. This will be very important in sampling, because you want, let's suppose you have a sample, you have sample 1, sample 2, sample 3. You know that samples are vectors. Okay, you have some data point 1, data point 2, data point 3. Now you want to see this, is this data good enough? Okay, let's suppose S1 and S2. If these things can be somehow merged linearly, if they can come up with S3, then we can remove S3 point. Okay, this is one example in sampling. One example can be, if I take features x1, x2, x3, something like this. Okay, these will be a set of features, they have set of values. If I can come up with this feature x3 by just using x1 and x2, I can remove this x3. Okay, so because these things are linearly dependent, if they are dependent, I can remove some of the parts to make it the least possible. Why? It will have implications efficiency, in computational efficiency you can use less resources. It will have implications, you can do it very fast, speed will increase, and you should know that are these things linearly dependent or independent. Can I assume that this is clear for you people? What is linear independence and what is dependence? Okay, so for this, after this, once you know what linear independence is, once you now know that there is a row picture, there is a column picture, we'll now move to the methods. Okay, we'll see methods of solving these equations, methods of solving the equations. I would love to stop here because we'll take this in the second session. I'll take some some questions from you. So in here, if you see, so today's lecture, if I just summarize it, it was focused on, when you see these equations, if they are in 1D, 2D, okay, you should imagine them in a certain way. So we saw a row picture and we saw a column picture. Okay, and most of the times you should go with this column picture. Okay, this is very easy to visualize. Then we also saw what is a span, and we saw linear dependence or independence. Okay, we saw this, and now all of this sort of set the foundation for you people in order to see the fundamental problem of algebra, how to solve that. And now we'll see the methods to solve those. But the first thing that you should be well versed with is these things. Okay, row picture and a column picture, a span, and this linear dependence and independence. Now the thing is, if you know this very well, so what we can do is we can just go to the matrix multiplication, all these things, and I'll show you from these basics how to basically learn matrix multiplication, because you might have seen people doing matrix multiplication in certain ways. So just covering that. So if you saw this 1, 2, 3, 4, if I give a vector 1, 4, usually how you see matrix multiplication is done is you go like this and then go like this. You say 1 multiplied 1 is 1, and then 3 multiplied 4 is 12, and then you write 13 over here. Then you say 1 multiplied by, again you go something like this. Now you take this and you go again. Okay, this will be a vector. So you go 2 multiplied by 1 is 2, 4 by 4 is 16, so this is 18. That's how you come. And I just showed you today one more method. So I said 1, 2, 3, 4. If you have this is 1, 2, 3, 4, and 1 and 4. So basically you can take this as a linear combination. You can say 1, 2, take 1 of this, plus take 4 of these, multiplication by columns. Okay, take 1 of this and take 4 of this. That's what these numbers say, and then you land the answer. So this is 1 by 1, 2, and plus this is 12, 16. Again you landed at 13, 18, something like this. Okay, so now you saw that why is matrix multiplication done in a certain way. But I'll show you all the methods that I have learned along the course. And this matrix multiplication is a huge problem in GPUs. Why? Because most of deep learning, most of machine learning is done in matrix multiplication, and you want to optimize this matrix multiplication. You want to optimize this. Okay, if you optimize this matrix multiplication, you are doing a great job, and the point is that you will increase the efficiency. Now I just showed you one method by just taking one column at a time. Okay, and all the GPUs mostly work on matrix multiplication. Okay, because graphics work in matrix multiplication. I'll just give you a background story. So they usually do matrix manipulations when you play games. So they just take matrix, multiply it, and then take the scene somewhere else. Okay, but when the deep learning, machine learning was discovered, when people are working on it, they also saw this matrix there. They saw, oh, matrix multiplication happening. So we have a matrix getting multiplied to somewhere else. So can we use GPUs on this? Okay, so they started using GPUs for performing deep learning computation. Okay, I think Hinton was the first guy who proposed this. We can use deep learning because if you see graphics part and if you see deep learning, they are somehow manipulating these matrices. Okay, so Hinton actually was, if I know the story, so he was in a conference and he was asking people we can use these GPUs. Okay, and he suggested use NVIDIA GPUs. And the story goes like this. After that, he told NVIDIA, I have told some 1,000 machine learning engineers to use your GPUs, give me a free GPU, but they didn't take him seriously. And after that, I think he contacted Jensen after that people are using GPUs now, and after that he got the free GPU from NVIDIA. Okay, and Hinton was, I think, among the first people who thought that we can use GPUs for this computation, because most of the computations are matrix multiplications. Okay, and when you see these benchmarks also, you might have seen people checking phones, okay, how much good it is performing. It usually is some matrix multiplication. It is performing some matrix multiplication, some checkered, and they have a benchmark specific thing. Okay, because they check if I play games, what's the frame rate, what is this, everything goes down to the matrix multiplication. And we'll maybe see the architecture, why is it better to use GPU for this matrix multiplication, and there are optimized ways to perform matrix multiplication. And the best algorithm, I think, is order n cube. It's and 0 point something. This is the complexity of that matrix multiplication algorithm. If you can come up with a better matrix multiplication algorithm, you will definitely win an award or something, because you will optimize GPUs and everything in that. I think recently we got an algorithm which AI discovered for matrix multiplication. Okay, but I just wanted to give you, when you see a matrix, what should pop into your head. And I hope this lecture will serve as a stepping stone, and by the help of which you will be learning more algebra, and you will be learning much what goes underneath these computers, and how to create graphics, how to maybe do machine learning and deep learning and stuff like that. Okay, and I think in the next class we'll take these methods to solve these equations, and we'll keep it quite short, because most of the times you won't solve the equations. There are packages, NumPy has the package, and PyTorch, everything has the package. You will just write dot something and it will solve that for you, but you should know what is going underneath the hood. And in your assignments, expect to write this code. I'll just tell you, write Gauss-Jordan method. Okay, if I give a matrix, you should find the values of this. If I give you an equation, set of equations, you should be able to solve it. Write some method, and maybe write an efficient code, and we'll check your code for efficiency also. Okay, I'll stop the recording over here, and I'll take questions if you have any.